Hey guys, we're in chapter 15. How are you guys doing? I'm still grading your tests, so bear with me. But, let me grab my little whiteboard here that my children drew on again. Children drew on it. Let me talk about an introduction to sound waves here. I'm just recording a video because we have to figure out a time that we can get together in Zoom meeting later in the week or something. But I'm recording a video for now. I figure it'll be probably better if I do a couple videos instead of just trying to Zoom meeting everything. Sound waves. That's what we're talking about this chapter. If you remember from last chapter, the regular waves, any kind of waves are just there's a crest, there's a trough. All of the characteristics of waves apply to sound waves. But sound waves are specifically pressure waves. Think of sound waves as pressure waves. And there's, because it's a pressure wave, it's like pushing and pushing and pushing and releasing, pushing and releasing. What happens when a sound wave travels through something is it travels through the air, and it travels through, let's say, the air. They have air particles, and the energy is passed from particle to particle. I don't know if you guys remember what conduction is from back when we did the thermal energy chapter and everything. Conduction and convection, you guys remember those? Convection was when the actual material moved, like hot air, like let's say somebody has hot breath and they go and breathe their hot coronavirus breath on you, and they breathe on you, and you can feel their breath. That's convection because the heat actually moves, and their stanky breath just blows all over your face. Conduction is when it's passed from particle to particle, when you have like a glass of coffee, a mug of coffee, and you're holding this out of it, and the heat goes through the coffee into the ceramic mug, and then from the ceramic mug into your hand. It's passed from particle to particle. They're like, here you go. You guys remember we sat in class and I had you guys pass a marker from person to person? That's conduction. And so kind of like conduction, the way energy in the form of heat, thermal energy, moves by conduction is the way that sound waves work. Sound waves are passed from particle to particle. The energy is passed from there. But you can think of almost like dominoes or like a car crash. You have one thing here, and that energy, the sound energy, because sound's just another form of energy. You have thermal energy, you have radiant energy, you have sound energy as well. And so you have this particle with sound energy, and they're evenly spaced apart. Picture all these particles just like, if I were to draw it, it's like just evenly spaced apart. You have all these particles just kind of evenly spaced apart. Well, what happens is when a sound wave carries energy, these things, they're pressure waves, so it presses one particle against another, and it squishes them together, and it bumps, and then as they bump, you're creating an area of compression, right? Instead of being evenly spread out, bear with me, they become squished together in a particular area. Okay, so you can see that the sound waves, the particles here are squished together. What's happening is a pressure wave is coming from this side, and they're squished together, pushing together, and they're creating an area of what's called compression, right? Two particles close together. Over here, if we didn't have this is what would be the normal resting state, right? But a pressure wave has pushed these particles toward one another, and they create an area of compression. This is called compression, and you notice it's a farther, really, these shouldn't be here. There's an area of empty space here that maybe the next ones would be like right along this line. There's a larger gap of empty space, and that's called an area of rarefaction. So you have an area of compression where they're compressed together, and an area of rarefaction. Well, what happens is, as they bump, they have an area of compression. Well, they bump these ones over, these air particles over. So now those air particles fly over this way, and they bump the next air particles, and they could create a new area of compression. So you have compression right here, right? Compression right in the middle there. And then this area here is called an area of rarefaction again. And so it's almost like you'd see rarefaction. It looks like the word rare and then faction. Um, it's almost like what you'd expect from a pile up on the highway of rear-ending, and they keep sending it into one another. That's how sound moves. Bumping in, because they are they are squishing one another. And so if that's how it works, it's a pressure wave. In order for that pressure, you got to think about it, in order for that pressure to happen, what has to happen is some object needs to vibrate. Okay? That's how you make a sound. In order to make a sound, you need to make something shake or vibrate. Think of any sound that you make. Clapping. I didn't clap very loud because the kids are sleeping. Silas is sleeping right down the hall. If I clap loud, he's going to wake up. So let's do a little clap. Okay? There we go. That what happened there when you heard that little is that my hands hit one another and the surface pushed against one another and compressed together and shook. It shook the surface of my hand. If I were to hit the table, okay, I'm hitting the table and the table compresses a little bit and moves back out very, very slightly. You can't really see it. And that creates a pressure wave that we can hear. And that wave expands off of there and it goes all the way to my ear. And my ear has little devices in it that detect sound, that detect pressure waves. I mean, you can even think of them. That's essentially what a microphone does. When you sing into a microphone, it has like this piece called a diaphragm, and the diaphragm moves back and forth. When you sing into it, you're creating a pressure wave, and the diaphragm moves back and forth, and there's a metal plate that senses those different pressures at different times, and then the wire interprets those as sounds, and that's what happens when you do that. Well, your ear does the same thing. Your ear senses all the different pressure waves at different times hitting the ear, and it senses all of the different sounds that are made, and then goes through the cord, which is your nerve cord, into your brain, and your brain interprets those. Okay, so again, there's this your tympanic membrane, your eardrum gets these. It's almost like literally like a drum that goes back and forth and senses these pressure waves. Same thing in a microphone, like a diaphragm microphone, and then it moves all the bones in your ears, the incus, malleus, and stapes in your ear, and those are connected to your nerve cord, which goes to your brain. Your brain interprets those signals as what I'm saying, and not only that. Think about how crazy this practice is. I am, let's say we're in the same room together, and you can actually hear me. I say hi. Me saying hi, the sound waves are vibrating the air because actually first, let's go even farther. First, what's happening is my larynx here is moving back and forth, creating pressure waves, okay, creating pressure waves inside here based on the muscles. And by the way, that's what determines how high or low you can speak, which we'll talk about that later, is the strength of your muscles, the thickness of your muscles. If you have thicker throat muscles, then they create a lower sound and they vibrate lower at lower speeds. If you can make a higher sound, they vibrate at really fast speeds, or they're able to vibrate at fast speeds. Generally, men generally have thicker neck muscles, and so they vibrate at lower frequencies, versus women generally have higher neck muscles that can vibrate at higher frequencies, so they make higher sounds. And so that's happening. These things are vibrating, and as I'm making sounds with my shapes with my mouth, making shapes with my mouth and shapes with my tongue, and those are different shapes that I'm making to produce different sounds, like ooh, ah, a, ba, different things with my lips, my tongue, and the shape of my mouth. Think about that. All the sounds that we can make are based on making our lips a certain way, making our tongue a certain way, and producing different shapes in our mouth, like o or ah, and then the sound is just ah coming out of our throat, our larynx, and so that comes out, and that sound wave goes out through the air, and I say hi, right, and that sound wave goes out through the air, bumping all those particles as they go, and then what happens is it hits your ear, and your tympanic membrane in it in there senses the pressure wave, the different to high. It goes, the pressure wave goes in and out, and it moves the bones in your ear, and the bones in your ear at a certain frequency they move, and that pressure wave is sensed by those bones in your ear, and they send the signal to your nerve cord, the pressure wave. Your nerve cord brings that pressure wave as like an electrical current into your brain, and now your brain senses, okay, there was a pressure wave, and it interprets that pressure wave as a sound, the sound high. Not only that, then it actually goes and looks up in the files, in the files that what those sounds, puts it together, it makes it a word, high, and then it looks at the context of the word. Okay, what does that word mean? High means it's a greeting, and it looks up and then what are the appropriate things to say back? And you say, hey, back, okay? All of that happens. Think about how quick it happens. Hi, hey, that's how quick it happens, right? But all of those processes are going along between the hi and the hey. Is that whole entire thing. Your brain is interpreting all of that stuff in split seconds, and that pressure wave is being brought over. So that's what a sound wave is. And you can see on page 404, you can see that bell there. On the top of page 404, you see the bell. When it's not ringing, you can see that there's the steady purple line. But in B, you've rung the bell. What do you do when you ring the bell? You shook it, you hit it, you created that shake, and that shake has created areas of compression and rarefaction, right? Condensation areas and areas that they're not condensed, and so you see those areas as it's pushing those air particles around. We'll do a little bit more, only 12 minutes, so we're good. And so, so there's higher pressure areas and lower pressure areas. You can see that in A is a longitudinal wave. When you look at the bottom of 404, A, B, and C, you see A is a longitudinal wave. And you see there's areas of compression in there as that thing moves along. But so the pressure variation that's transmitted through matter, so pressure wave sent through matter, we call a sound wave. A sound wave is just a pressure wave. Another important fact in page 404, so the speed of sound in air depends on the temperature. So this is important. So the speed of sound, how fast sound goes in air, depends on the temperature. Remember, if you remember from last chapter, we had an example where there was where we calculated the speed of sound in air, and it came out as like 343 meters per second. And that's the speed of sound in air, 343 meters per second at room temperature. It actually depends on the temperature, though, because it says it increases about 0.6 meters per second for every 1 degree Celsius in room temperature. So that means the hotter it gets, the warmer it gets, the faster sound will go. And so the hotter you get hotter and hotter, the faster sound will go. But sound actually travels fastest through solids, liquids, and gases. They travel different speeds, and it travels actually slowest through gases. So if I were to say something to you like, hey, through across the room, you'd actually would hear it earlier if I had said it through a different surface. Like, for instance, if you were making noise through water travels, the liquid, in liquid, sound travels faster. And in solid, it actually travels fastest. Here's the reason why. On a particle level, think about what the particles are. In a solid, they're right next to one another. And so that pressure wave is carried by, and it's really easy for those particles to carry them to one another. In a liquid, they're still connected to one another. In a gas, they're all flying all over the place, and they hit one another, and then they transfer that energy when they hit one another. But how often do they hit one another? Not very often. Well, very often enough, but it takes long for them to hit one another. So there are great variations in the speed of sound in different states of matter, and this is a really easy way to test it. And I actually want you to do this. This is part of your homework. Okay, if you can, this is an optional homework that I really want you to try. You have to do it with somebody though, so hopefully you have someone in your family that can do it, and hopefully you have a chain link fence. It's easy stuff in chain link fence. Go to somewhere with a fence, like a chain link fence, and have somebody go as far away as possible on the chain link fence, and you put your ear to the chain link fence. You put your ear onto like the metal of it and have somebody stand far away, and they're gonna bang on the metal of the chain link fence, not like the chain mesh part, but like the actual pole. You put your ear on the pole, and they're gonna take a stone and they're gonna tap 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 on the stone. And if you're far enough away, if they're like 5 feet away, you're not gonna notice a difference. But if they're far enough away, you'll actually hear the tap in this ear that's against the metal pole. You'll hear it a split second before you hear it this way. Okay, the reason why? Because it travels fastest through that metal to your ear, faster than it does here. Again, you have to be far enough away for it to make a difference. Try it. Might work if you have a big enough backyard with a fence in it. Very importantly, though, sound cannot travel. Sound has to travel through it because it's a pressure wave, and the pressure is carried by a particle bumping into another particle, kind of like conduction. Sound cannot travel through space. It needs a medium to travel through. Think about the parallels of conduction here, because conduction, heating by conduction, cannot, or even convection, cannot happen in space because there are no particles. Conduction and convection must both happen with particles, moving. Either convection with the particle itself moving, or conduction with the particles passing into one another. Sound is really like conduction of heat. And because the sound is carried by a particle, the sound energy is pressure carried by a particle, it can't move in space. So it's very interesting that there is no sound in space. In the 1980s, there's a movie called Alien. I think that was 80s. Might have been the late 70s. There's a movie called Alien. And the tagline for that movie was, "In space, no one can hear you scream." And that was a tagline. In space, no one can hear you scream. And it's actually scientifically true. Not that really you could scream, if you took your helmet off, if you're an astronaut and took your helmet off, you'd have a lot more to worry about than screaming. But if somebody did, let's say they didn't die and they were yelling and even just talking, they could scream right near your ear and you would not be able to hear them because there's no way to transmit sound. That's why Star Wars, in the very first Star Wars, great movie, A New Hope, when the Death Star blows up, okay, if you go back to that, that is not scientifically accurate for many reasons, okay? First off, if you go back and watch A New Hope, they blow the thing up and it goes like this. It goes boom. The whole thing blows up and you hear this big boom, right? Two things make it inaccurate. First of all, light travels way faster than sound. So even if sound was able to travel through space, it would be like boom. Okay, it would be like that. That's like why we have, sometimes if you're talking to somebody and you see them clapping, it'll be like clap, clap, clap. That's what you'll hear if they're far enough away. Or if somebody, if you hear something like a car, I don't know, backfire or something, you'll see it happen before it happens. So first thing in the movie, when it blows up and it blows up and they see it, and then several seconds later they hear it happen. But even if that, I froze. Just keep listening. Sometimes my computer does this, it freezes. I don't know why. Just keep listening anyway. I'm almost done. So the first thing about the Death Star blowing up that isn't scientifically accurate is that it would, if you could hear it, it would be the explosion. You'd see it and then you'd hear it afterward. But even so, you still wouldn't hear it because sound can't travel through space. But it would be really, really disappointing if picture in Star Wars if you muted at that point in time. They were like, they have the rockets and all of a sudden the thing blows up, but all you hear is, it'd be like, okay, that's pretty boring. Be like, yay, it blew up. But it'd be anticlimactic. All right, the last little piece of information there is a reflected sound wave is called an echo. Okay, so, all right, so I would like, and so we need to use that. This is an equation. If you see that little equation there at the end of the paragraph on page 405, the top of 405, the equation, that little melty easel is called lambda. Lambda equals V over F. You need to use, that's an equation from last chapter, but we're still using it in this chapter. So I would like you to do number 1 and 2 for homework. I'd like you to do 1 and 2 and answer those. You can even just, well, actually, you can, yeah, why don't you just post it? You can post it. I'll create an assignment for numbers 1 and 2. All right. Thank you. Have a good day.